slide you have come across, which is the consequence of these four different kind of substitution procedures. So aromatic electrophilic substitution, aromatic nucleophilic substitution reactions you have already come across. Now at the moment we are focusing on two: nucleophilic aliphatic substitution and electrophilic aliphatic substitution reactions. So first we shall focus on this aliphatic nucleophilic substitution reactions. So substitution nucleophilic are of various kinds. So it may be a diverse methods. So I have highlighted a few of them here: SN2, SN1, SNI, similarly SN2 prime, SN1 prime, SNI prime, SN2CA, SN1CA, neighboring group participation, which is also called enchimeric assistance, TD mechanism, which is an abbreviation of tetrahedral mechanism, similarly ion pair mechanism. So these are a few, almost a dozen different mechanisms which are operated with aliphatic system. So aliphatic system, these three operate with a different kind of substrate. These three which are enlisted in the past are operated with a different system. The last two are operated with a different system, and we shall get the neighboring group participation for different substrate, TD for different substrate, etc. Ion pair mechanism is applicable to the first these three in a different substrate condition. You shall see in all these mechanisms substrate shall change. And similarly in electrophilic aliphatic substitution mechanisms, we shall come across a variety of different one in which our recipient acceptor shall be different in fact. So starting with the very first class, nucleophilic substitution reaction first. So let's see SN2, SN1 and SNI we shall discuss first. Then we shall switch over to SN2 prime. What is the difference between SN2 and SN2 prime? What is the difference between SNI and SNI prime? Similarly SN1 prime and SN1. So this is the first. We shall start with substitution nucleophilic bimolecular. So SN2 stands for what? This is S for substitution, N for nucleophilic, and 2 stands for second order kinetics. Mean it is a second order. So what it means? Whenever this reaction is done, a reaction is done. If you have seen in previous slide, a reaction is done between an aliphatic system that we are calling substrate, reacting with a nucleophile, which is a reagent. In fact, normally it is a nucleophile, is a nitrogen nucleophile, oxygen nucleophile, halogen nucleophile, sulfur nucleophile. Mostly this is inorganic in nature, but not always. Sometimes you have seen in aldol reaction this nucleophile is a carbon nucleophile. All right, so it may be different. It may be it may be heteroatom, or it may be a carbon nucleophile in fact. So anyhow, we shall have a variety of nucleophiles here. This is our substrate, this is our reagent, right? So two entities are reacting in these cases. So on such basis, we can say that dx by dt mean rate of reaction, change in the increase in the concentration of product per unit differential time is directly proportional to the concentration of substrate and the concentration of nucleophile. So this is a rate law. If we replace the sign of proportionality by equality, we introduce a constant small k, which is commonly called rate constant. So this is called rate law for this reaction, SN2. So in this case, we shall see systematically either when it is with respect to substrate, this is first order or second order. With respect to nucleophile, this is first order or second order or zero order in both cases. So this is a very systematic protocol that you have already come across, because both substrate and reagent, they are not same, they are different. So first method of protocol of chemical kinetic method cannot be applied. So what should be applied? The graphical method and half-life method cannot be applied here. That is applicable to such systems in which we are having two substrates common. Same. Here substrates are not common. So our reactants are not same, they are different. So we are supposed to go through keeping the concentration of one constant and change the other and then see what it affects the reaction rate. If the reaction rate increases with the same rate it is been increased in concentration, so that means it is first order. If it increases square time, it means it is second order. If it changes cube times, it means it's the third order with respect to that. And normally we rarely have this second order or third order. Normally it is zero order or first order. So in this case, when we take the concentration of substrate, if we double this, the reaction rate doubles. If we triple the concentration, then the reaction rate also becomes triple. So we have observed by uh, calculating the reaction rate by change in concentration of reactant, mean substrate and nucleophile, and we come to know it is first order with respect to this and first order with respect to nucleophile. So what is to conclude in such a case, that the order of reaction is first order with respect to substrate, first order with respect to nucleophile. So on the power we have 1 here and power 1 we have here. So this reaction is by experimental method, this reaction is first order with respect to substrate and first order with respect to nucleophile. It means this reaction is second order. And second order reaction mean in rate determining step. It proceeds with the proceed with both reactants, mean nucleophile as well as substrate. So this is the indication which is giving us the kinetic data is giving us these results. So anyhow, when we construct the mechanism, how this conclude? Mechanism conclude that this reaction involves no intermediate. The conversion of substrate into product is a single step method. It doesn't involve intermediate. If intermediate is involved, it shall be stepwise. But if it is completing in a single step, it is concerted mechanism. So in fact, SN2 is a concerted mechanism. No intermediate has been isolated in such reactions. So when there is no intermediate is being isolated, it means because if it is a stepwise mechanism, it definitely involves an intermediate, or more, maybe more than one intermediate is involved. So when no intermediate is isolated in SN2 reactions, so it means these are so such reaction which are first order to substrate and first order to nucleophile. So they are always showing no intermediate formation. So when this was, so it concludes that a transition state is important. So a transition state is definitely involved here. Now keeping in mind, we can draw a transition state. The key aspect in SN2 reactions is that our substrate have a X group. What is X? You have seen X is a leaving group. So we have a terminology here. This group which leaves this sp3 hybridized carbon is called leaving group. And any entity which approach this carbon in place of X is called a nucleophile or approaching nucleophile. So, and this has been observed that in SN2 reactions, the nucleophile always approach from opposite direction to leaving group. It is not possible that this nucleophile is approaching from same direction where this leaving group is leaving. This is important. Why? Or any nucleophile in SN2 reaction shall always approach 180-degree like this, 180-degree to this leaving group. It means this nucleophile is approaching at this position. Diagrammatically, this is presented in transition state. You see this bond R1, R2 and hydrogen, they are same presented. R1 along the plane, R2 along the plane, when I am changing the configuration, I have placed this X along the plane, so this R2 shall bulge above, it shall go above the plane. So this is above the plane, hydrogen behind the plane, same configuration. So X and Y we are taking along the plane of this paper or this screen. But these bonds, look at these bonds are not same. This bond is a constant line. This is a dotted line. This is a wedge head line. This is a wedge line as well. But this wedge is different from this. So there are four kind of lines presented here. I have already presented these things in earlier that if you are getting a straight line like this, it means this is a covalent bond. But if we are getting a wedge head, this wedge which is bold, so it shows that anything is above the, this is a covalent bond, but this covalent bond is above the plane to show 3D structure. And this is also a wedge, but this wedge is a pointing dotted. So this wedge is showing anything pointing behind the plane. So these two lines, wedge in this way or that way, showing the two substituent in opposite direction. One is above the plane, other is behind the plane. But what this dotted line presents, this dotted line shows that this is not a full covalent bond. This is a half bond. This carbon is half bonded with X, half bonded with Y. Because carbon, if you look at here, 5 atoms are attached to carbon. Carbon cannot afford to attach with 5 atoms. If it is attached with 5, it shall have 10 electrons in the valence shell. So 10 electron carbon cannot follows the, it cannot violate the octet rule. Octet rule is that any atom cannot have more than 8 electrons in their shell. This is true for first two periods. Hydrogen, helium, similarly starting from lithium to fluorine. This is true. So for first two periods, this is true. But for rest of the other, this is not true. Carbon family belongs in second group. So after lithium, beryllium, we have boron and then carbon. So carbon is lying there in second period. So it can have maximum 8 electron in its valence shell. So it cannot afford to make 5 bonds. But this X, it mean have a half bond. This is a half bond. This is one bond. This is one covalent bond. This is one covalent. Because this is complete covalent. This is covalent. This is covalent. Difference between this and that is this is along the plane of the group. This is above the plane, this is behind the plane. But they are all three covalent bonds. These are three covalent bonds, half covalent bond with Y and half covalent bond with X. What this indicates, this is a transition state that leaving group is leaving, making a half bond, and a nucleophile has also approached this one uh, making a half bond. So because if you remember in concerted mechanism, if you remember, you have seen in the beginning of this course, the bond dissociation and new bond formation takes place simultaneously. So in this case, what is happening, this leaving group is leaving at the time when the nucleophile is approaching this at the same time. So this is the transition state which presents. This is dotted line which shows that X and Y leaving group and new nucleophile approaching the carbon, they are having half bonds. So overall we have one bond, two bond, three and half, there's four bonds. So carbon is bonded with 4 atoms in fact. With 2 atoms it is bonding half, having a half bond order, and with 3 other it has full order. So overall bond order of carbon is 4, 8 electrons in the valence shell. This is what we call a transition state. The key of this transition state is X and Y. They are opposite to each other, perpendicular, and not perpendicular, but 180 degree to each other. This is the key of substitution in SN2. This is why it is called SN2. 2 stands for bimolecular, which show that it is a concerted mechanism. It completes in a single step. Concerted mechanism. This is all concerted mechanism involved by transition state. This is a transition state involved in SN2 reaction. And what happens in this? X was present in this case, but now y is present in the other side. So look at here. If this x is, let's say, first priority, r1 is second priority, r2 is third priority, what is this configuration? Hydrogen is behind the flame. So now you can decide this x is 1, this is 2, this is 3, this is anti-clockwise. It has a s absolute configuration. But now look at here. If this y is also a heteroatom, so it shall be a first priority, r1 is second, r2 is third. Now you see it is showing the clockwise rotation, so it is r. This was s, but now this is r. So we have observed a change in configuration. This is by terminology called inversion in configuration. Change in configuration here is related as termed as inversion in configuration. And this studies was done by a scientist called Walden. So this is also in literature called Walden inversion. So Walden inversion is mean because this is a tribute to Walden, because he worked in the mechanistic study of SN2 reactions a lot. So that's why this is called Walden inversion. So on the contribution of the Walden. But this is in fact an inversion in configuration. How a change in configuration taking place, S converts into R converts into S. So this is the normally we observe in SN2 reaction. Keeping in mind it is not the optical rotation we are talking about at the moment. We are not talking about the inversion in inversion in optical sign. We are talking about inversion in configuration. What it means? Look at the difference. See, R1 and hydrogen. R1 is along the plane. Hydrogen is behind the plane. R1 is along the plane. Hydrogen is behind the plane. These two atoms are at same position. No change in reactant and products. But look at here. R2 is along the plane, but now R2 is above the plane. Here x is above the plane, here y is along the plane. So x and y are opposite to each other. This is now the configuration is changed. These two are having same position, but these two groups, these two R2 and X, R2 and Y, so they are opposite to each other in both cases, to reactant and product. This is termed as inversion in configuration, right? So, and this is also commonly called Walder inversion. This is the overall mechanism of a SN2 reaction. And but keeping in mind such compounds in which we have R2 is hydrogen, R2 is hydrogen, mean primary carbon system. If we have this carbon only bounded with one alkyl group, it 100% proceed via SN2 mechanism. If let's say we have this R2 is not hydrogen, this is alkyl group as well, then it is not 100% going through SN2 mechanism. You shall see these studies in mixed SN1, SN2 and in ion pair reaction in much more detail later. But at the moment I shall say primary carbon. Primary carbon, we have one alkyl group attached. This R2 is hydrogen, this is already hydrogen. So if it is a primary carbon, substitution is taking place with a nucleophile, follow SN2 mechanism. It shall always be 100% proceeding via inversion in configuration, but we must have a substrate primary carbon. If it is secondary, we cannot guarantee. If it is tertiary, this hydrogen is replaced by another alkyl group, then it doesn't proceed by SN2 mechanism. So primary carbon 100% proceed via SN2. Tertiary carbon proceeds 0% with respect to SN2. What if we have a secondary carbon here? As I presented, R1 and R2 are alkyl group, it is a hydrogen. Then we cannot 100% say it is 100% proceeding via SN2 mechanism. So we cannot guarantee. So it depends upon what these two groups are in fact, right? Various parameters are there. We shall discuss the factors which affect SN1, SN2, and SNI in upcoming lectures, in fact. Anyhow, you should focus. SN2 mechanism always proceed with inversion in configuration. Primary carbon always undergo 100% SN2 mechanism. Tertiary, if it is, all three these are alkyl groups, it doesn't proceed via SN2. So 0% it proceed via SN2. But if it is secondary carbon, then it is a mixed behavior. It follows SN2 and SN1 both, depending upon the reaction condition that we shall discuss after completing this mechanism. So underneath, I have presented something very interesting, but keeping in mind this reaction is concerted, single step. This what I have presented as a transition state, it doesn't mean this is a step. This is not a step. This is just elaboration that this converts into this in a single step by passing through this transition step, right? So this is a reactant going to form product passing through this transition state. This is not an intermediate. So it is not a two-step, it is a single step, concerted. But look at the underneath. I have presented here in the center a Z atom. Z is not carbon in this case, keeping in mind. Z is silicon or tin. Keeping in mind carbon, silicon and tin, they are in same group. Carbon family. Carbon, silicon, tin, lead. All of them are in same period. In same group. They are belonging to carbon family. So carbon, silicon, and tin. But the chemistry which is being exhibited by silicon and tin is entirely different from carbon chemistry. So if let's say in the center here it is not carbon, it is tin or it is silicon, then the chemistry is entirely opposite. Why? Let's say if this Z is silicon or this is tin, tin commonly called stabium. So this is in fact, sorry, this is stannum. So this is SN, it is commonly called tin, but it is stannum in fact. So this, if this Z is tin or stannic, any of them belonging to carbon family, if it reacts with nucleophile, mechanism is 100%. If it is carbon, it follows concerted mechanism. We call this SN2. But if in center here it is silicon or tin, it doesn't follow SN2 mechanism. It is first order with respect kinetically. Let me conclude. Kinetically, it follows this mechanism. It is first order with respect to substrate. It is also first order with respect to nucleophile. Now you see, so if we write, the very first step is slow rated, the second step is the fast rated. And keeping in mind, this I have presented in parentheses, this is an intermediate, this is not a transition state. This is very surprising that the kinetics, this reaction is also second order. This concerted mechanism is also second order. For the rest, first order with respect to substrate, first order with respect to nucleophile. These reactions are also first order with respect to substrate, first order with respect to nucleophile. So it is also second order overall. This reaction is also second order. but this is not following SN2 mechanism. Why? SN2 mechanism proceed via transition state. But look at here, what is happening? In this case, we are getting Z atom, silicon or tin is making 5 bonds. You see, this bond with X and bond with nucleophile, these are complete bonds. We are not presenting dotted line here. But sorry, this is one covalent bond, this is second covalent bond, this is third covalent bond, this covalent bond is above the plane, this covalent bond is behind the plane. It is making 5 bonds, but they can afford to make 5 bonds, keeping in mind the position of silicon and tin in periodic table. Silicon is in third period, tin is in fourth period. If you look at silicon and tin, both involve d orbital. So in this case of silicon, d orbital is completely empty. In case of tin, 4d orbital is completely empty. But in carbon, the valence shell doesn't contain any d orbital. So the nucleophile, in this case, what happens? The nucleophile donates electron pair in d orbital of the valence shell. If it is tin, it shall be a 3d orbital. In case of tin, it shall be a 4d orbital. So this nucleophile accommodates this electron in d orbital, which is vacant, 100% vacant, empty. So this is how it makes a bond. X doesn't leave, Y make a bond. So when Y is making a bond, this Z, which is tin or silicon, it carries a negative charge because it has 10 electrons in the valence shell. These 2 electrons are coming from nucleophile. So it is making first a bond with the nucleophile. Then in next step, this X leave with the electron pair. So zinc, this Z carries 8 electrons again. So what is happening? We are getting an inversion in configuration as well. But mechanistically, this reaction is done in 2 steps. Keeping in mind, this is an intermediate, this is not a transition state. In transition state, we are having half bond with a reactant and half bond with a product. So if I present this bond with a red color showing this is a bond with a leaving group, this half bond with green color means this is a bond with a nucleophile. So half bond here, total 4 bonds. But you see here there are 5 covalent bonds. This is something which is hypothetical. Transition state is always hypothetical. But this is something which is an intermediate. If you remember, I have presented in the beginning of this course that an intermediate is something which is having a real life. The life of this can be in nanosecond, in picosecond, something very minute time, but they does exist. Transition state doesn't exist. So transition state is something hypothetical and intermediate is something that we call real. So if we are focusing on silicon and tin, they follow this mechanism because d orbital is involved in them. So nucleophile accommodates this electron pair in d orbital in fact. So this is the difference in mechanism. Carbon, tin and silicon, they belong to same group. So the silicon and tin chemistry is entirely different. It follows a second order kinetic. It follows a inversion in configuration. This is the same. You see, product is same, reactants is same, but the mechanism is different. One involve a transition state, other involve a intermediate. So here the first step is a slow rated, second a fast rated. So it means rate determining step is the first step. In first step you see nucleophile and substrate both are reacting. So it is first order with respect to both. So it is having second order kinetics as well. So inversion in configuration taking place in both mechanisms, but second one with silicon and tin, it doesn't follow SN2 mechanism.